Testing 1 2, testing 1 2. Okay. It's okay. Good afternoon. All right, so it's a morning. So, who is was 6 years here engineering? Yeah, also. Yeah, I mean, sometimes we take things for granted, eh? You put in the work, you sweat, but then you don't really celebrate the accomplishments. So always take pride in who you are and how come you've come. I mean, kwenze nangu mwenze na mu first year. Sibari kote. Civilies munafika hapo pa. Okay, so celebrate your accomplishments as often as you could. All right, so we're going to look at a very interesting topic today. Also going to just use my phone. What were we doing last week? Or is it the other time we met? What did we do? Surface water hydrology, we talked about surface runoff, not so. What are some of the key points you remember about the surface runoff? What really came out? What was that thing that you never knew? Now you do, and it will take time before you forget it. Anything from last week's class? Engineers? Yes, anybody? Yes, sir.
The two major categories or factors that influence surface runoff, which are climatic change and the catchment characteristics.
Okay. Climatic and catchment characteristics. Great. That's a good way of classifying the two. Anybody else? They remember anything about what we had? So usually when a lecturer asks what you remember, the more you're quick to answer that question, the more I feel like they don't need a quiz or a test, these guys. But Muliziso, I'm like, my guys. We need to wake them up, eh? Anything else? Okay. You know how quizzes work, right? We don't mention, yeah? Because we expect you to just know and be up to speed with everything. Okay? Eh? Hey, a bunch.
Yes, we also talked about what under the catchment characteristics.
Uh-huh.
The catchment area. So we said that the more the area, the runoff increases. Yeah, I mean, reduces.
So the more the area, the bigger the area.
The bigger the area, the less.
Anybody else? Yes, sir. So what about the roundness? How does that affect runoff? Does it increase? Does it reduce runoff? You're talking about the catchment characteristic of it being round, right? Not so. The land use. Oh, okay. What about the land use? What happens? Okay. Okay. Anybody else? Yes, madam. Slopiness of a catchment. What about it? So when you mention that characteristic, state whether it increases or reduces, or how does it affect runoff? So the slopey an area is, the more runoff. More slopey? What happens to the runoff? Does it increase or reduce? More naka. Which notes are those? She says that it reduces. Infiltration reduces, right? Because if it's sloppy, you expect water to just flow with, of course, gravity, gradient there. It makes it easy to just run through. Are we together? Okay, I can see people are not studying. What is drought? What is a drought? Yeah? Yes, sir. Little or no water. Okay, that is one way you can put it. Another way, yes, sir.
Let's say in areas where there is usually
Okay.
when there's a period where it's prolonged dryness, that area doesn't receive enough rain for that.
Rain. So Zambia just went through that phase, not so? And you could see, you've seen how that affects a lot. Power generation, because as engineers, you have gone to sleep because you feel like you have all the waters in the world. But part of being an engineer is you being able to forecast. If this is my stream, weather conditions do change. There's global warming. There's just a climatic change that will just happen within, you never know what happened. So we never planned ahead, all right? And so now we're going through a phase where, one, it has affected how much power we're generating. And if we can't generate power, it cripples a lot of things. It increases the cost of doing business. And if this is true, the effects are mostly felt by the consumers, such as, ourselves. But then this topic is a little bit tied to producing water, producing electricity. But then there are many other reasons why we need to be interested in the drought, okay? So I'm going to try to define what this is in addition to what the two gentlemen have. And then after that, we'll talk about why we need to study. So a drought in hydrology has a terminology known as low flow studying, all right? So it's a low flow, then how does that affect our being? All right, so let's define drought, what a drought is. Drought is defined by looking at the balance between water supply. Drought is defined by Drought is defined by looking at the balance between water supply and demand. Drought is defined by looking at the balance between water supply and demand. Whenever human demands for water exceed the natural availability, whenever human demands for water exceed the natural availability of water, okay? Whenever human demands for water exceed the natural availability of water, the result is drought. The result is drought. The result is drought. Full stop, we continue, can put a different point maybe. It can be caused by too little precipitation. What is precipitation? Forms of precipitation? Yes, sir. Okay. That should be first year hydrology, not so? So it can be caused by too little precipitation. It can be caused by too little precipitation over an extended period. Over an extended period. Over an extended period. But drought can also be caused by increased demand for the available supply. Increased demand for the available supply. Increased demand for the available supply of usable water. Of usable water. Of usable water, even during periods of average or above average precipitation. Even during periods of average or above average precipitation. Okay, so what they mean is that the definition you've given of having little or no rainfall is one way you can define it, but then also you can still have precipitation, you can still have water, but if there's a higher demand for that water, then you're experiencing a drought. There's just way too little of water that can go around. Okay? Need to find a connection here. There's always someone who's calling when I'm lecturing. Okay, so another point. From these definitions, from these definitions. Our concern in this will primarily be on river flow analysis. Our concern will primarily be on river flow analysis. Our concern in this will primarily be on river flow analysis. Which when applied to droughts, which when applied to droughts is termed low flow analysis. Low flow analysis. Low flow analysis. Okay, are we there? All right, so let's talk about the application of low flow analysis. So I can just say application. If you've written that word somewhere. Application. Application. So low flow analysis has many practical applications. Low flow analysis has many practical applications. Low flow analysis has many practical applications. Comma. Some of which are briefly introduced here. Some of which are briefly introduced here. Some of these are briefly introduced here. Okay, so one, or A, reservoir operations. Why do you think it's important for us to study the least amount of water a river can have if you're going to talk about operating a reservoir? So under this topic, these are some of the questions that you should expect. Why is it important, or what makes low flow analysis important if we are trying to relate it to operating a reservoir? Anything that comes to mind? Why do we need to know how much water a river or a stream can have? Yes, sir. Mm-hmm.
A company or an organization that looks into the water use there.
Mm-hmm.
So whereby when they said Moses was given allocation about I don't know how many cubic meters of water. So there needs to be someone who oversees the operations and the water that is being used, so as to not lead to drought. So they can maintain certain level of water that is needed for.
Okay. Are you talking about the Zambezi River Authority?
Yes. I'm just saying
Yeah.
There needs to be someone.
Okay, I get your point. Anybody else? Yes, sir.
So observing the amount of water that is in a reservoir is important because we don't want to have no water at all. So we just want to keep more or less of a safety stock.
Mm-hmm.
To say this is where we need to control the use of water, and this is our based.
Okay. Anybody else with a different view? Anybody else with a different view? Others? Ladies? We don't feel like talking today. Madam? You want to throw in your 2 cents? No? Yes, sir. Zambia River Authority?
So this is important to ensure reliable water supply during droughts situation. So if you study that, you're able to know or to store water that can be utilized when you face such a challenge like this one.
Okay. All right, great. Just in addition to what you've all said, so there are many reasons why we need to study low flow or the lowest levels of water that you can find. This is what this just means. So this is low flow. So your lowest values of flow in a river, you want to understand that stream and how much of it can accommodate. So specifically for reservoir operations, so you see, when water is coming from the upstream and then you've got your dam, which I'm very much sure you understand because we cleared, or at least had a SAP, some of us, but we cleared. Let me say this. It is very hard for me, personally, to see a third-year student failing to clear a course. You are in third year. I mean, you've done first year, second year. So you make my work or any lecturer's work in third year very hard. I don't know where it comes from. I know I've been in your shoes before. Last year is just like, look, I've cleared before, so I don't think I need to put in as much. And also you're just tired. You're looking at the same faces all the time, same lectures all the time. You're only happy when you've got freshers, but even that gets old at some point. My point is, you're almost done. There is no need for you to come for a SAP. We're soft now, pass a SAP. And then waboafiru kasap foot. It's mental torture because I'm thinking this person is in third year. Obviously, when the bulk of the colleagues are graduating, they just have to be a part of this. But then I'm looking at what you've written. So I'm conflicted. Me being a reasonable person, let me reason so that everything flows well for you. But then also I've got a profession, I've got a career. I need to only ensure that people that are clearing are able to go through. Make my work easy, guys. Concentrate in class, study. We never bring anything out of this college. Any question that I'll give you today, tomorrow, even the last semester, last year, those questions are still there. And then someone writes, you'll be like, ish, who hurt you, man? Don't do that. Okay. So the dam, if this is your upstream and water is coming from the Kaleni Hills, you want to control the lowest that you can have in your Zambezi River, for instance, because the downstream is making use of that water as well. Are we together? So if you know that, well, our Zambezi River only gets to so much, then how do you navigate? How do you plan? Because there's always a gate valve somewhere that you allow water to go through to the other side. Under dams, we talked about the upstream, you probably have your highest levels, and then on the downstream, you've got just lower levels. So based on what you're having on the upstream, it informs what you leave on the downstream, all right? So it's a very nice, well-written paragraph just to expand more on that point in the module. If I can read something about this. Where a reservoir is used for, don't write this, you've got the notes. Where a reservoir is used for water supply or irrigation purposes, it is important that the flow out of the reservoir is controlled. in such a way that the needs downstream are met. So you cannot just impound water because you've got a project going on here. You need to leave some of it that goes because there are people after your dam. All right. Another well-known application to low flow analysis is the hydroelectric power stations. Hydroelectric power station. Power station design. Power station design. Why do you think when you are about to design a power station, a hydropower station, why do you think it's important for you to know the lowest levels that stream will give you? Let's go, wangu guys. Why do you think it's important? I'm usually, yes sir.
Personally, I think it's because maybe, for example, like the situation we're having right now,
Mm-hmm.
you have low flow of water.
Mm-hmm.
You need to take precautions. Maybe, let's say, if we're going to have flow of water at this level, maybe it's very low.
Mm-hmm.
You need to have maybe another alternative for us to provide electricity.
Energy or source. Yes sir.
I think it also help us in determining what machines can make it happen. For
Okay.
instance, we can put huge turbines
Mm-hmm.
in a point where we have low flow water.
You do have a point. I saw a different hand. Yes sir.
Yeah, like the situation that is happening now. These turbines are moved by a high volume of water.
Mm-hmm.
So we need to assess the lowest point
Mm-hmm.
at which our stream or our flow of water runs,
Mm-hmm.
so that we know in the most critical point
Mhm.
can our turbines run. Like
Yeah.
at the moment, the hydro station is running is powered just by one turbine.
Mm-hmm.
So that is rectified by the flow of water.
Yeah. You all do have points. So just read more, expand more. See, those points that you've mentioned are just some of the few that you can have. Under this topic, there's just so much that you can read about reservoir operations. And so I always tell students that do not restrict your studying to just the modules. Go through the modules, but always just expand your thinking, okay, around certain issues. They studied low flow for the point of our power generation. And that is the reason why, even as early as January, they were able to tell you that by June, July, you're going to have critical low levels of electricity. Because they knew, and they have studied, that when the fact that we don't have so much rain at the moment, these levels are just going to draw to a point whereby our design, like you've said, can only produce so far. And if it's only producing that much, how do we ration for people to have? Okay? Yes, sir.
Like, indeed that you're saying they studied, but then the allocation that was given is for the whole year. So again, it's the misuse of the company that they misused the water, because the allocation that was given was for the whole year. I'm sure the water that was given to them to use was for the whole year. It wasn't for a specific period, like 3 months.
Mm-hmm.
So again, it was more up to the people who are using who are operating the reservoir itself.
Do you know where the problem is? You can have water enough right now and say, you know what, if conditions don't change, I'll supply the whole year. But conditions change. So the rainfall does not fall as much as you thought it would. So that tag of we can produce for the whole year is no longer there. That's one. Two, we can't save electricity. And I think this is a project that people are still trying to crack their heads around. Is there a way you can produce electricity as the waters are running and then just store it like in reservoirs? Like readily made electricity. Okay, so that's one point. And then if you're going to go a little bit away from academia and you go political, our power supply company, ZESCO, has already MOUs with other countries who they have been supplying for the longest of time. And usually those MOUs will state it doesn't matter their conditions unless stated or otherwise. And these are MOUs. I mean, you never really know the clauses that they put in there. But if you agree to supply South Africa for this much, South Africa is expecting that amount of energy source. If you fail, you're compromising your bilateral relations with that country. And then it's hard for a current government because Wangena Poche on the seat, the previous guys are the ones that made that deal. You can't move in and then start saying, no, we don't want to work with that MOU. They signed that MOU. So you are here as a new government, as a new boss, you need to work with what was already signed. One of the toughest jobs we can ever find at the moment is being the managing director for ZESCO. You know that guy, the Mapani guy? But again, he's an engineer, and these are problems that we are giving you in school so that when you're in those positions, you don't feel like committing suicide. Because for him, I don't think that brother is even on social media. If he is, he's not the one reading the comments. It's that bad. Because people will literally throw death threats on you, on your kids. When you don't get a business, you know what I mean? So it's that dire. All right? So it's a little bit more complicated. You could plan for it, but one, the weather conditions happen, and then there are also just these, relations that you've already built. All right, but then good observation, sir. So another reason why we need to study low flow analysis is pollution control. Why do you think it's important for us to know or study the lowest levels of water? If we paid much attention to, I think, water supply and sanitation in second year, there was something that we mentioned about pollution control and streams and rivers. I would want that connection. It actually exists even here at NRDC. Why do you think it's important for us to study low flows in a river or a stream where pollution is concerned? Yes, sir.
Yes, under pollution control, I remember in second year, there's a place we visited where the wastewater used to go. When they remove some unwanted materials, then again it will be taken back to the river.
Oh.
For the use of some.
Okay. Did we get what he said? Anybody else with a different view? Yes, sir.
So what happens is that there is a thing flow that self-cleanses the river. Then when the sewers are being wet, or I can say the wastewater is being cleaned, it is discharged into the river, then it's more like self-cleaned by flow. So if there's low flow, we need to control the pollution.
That we are putting in the stream, right? Just precisely that. For now, at this level. Yes, sir.
Also preserving the natural resources such as air, water, and also the soil. Also maintaining the ecosystem balance.
Yeah, great. So again, on this point, there are many other points and factors that you can put. You guys are done with school. I do not even need to emphasize how important it is for you guys to know how to write. So like when you're writing, put your mind into it. I'm usually bad at reading, but when it comes to, because it'll just be about 4 points. So I'll take my time to read through your thoughts. And if I'm not sensing what we are discussing or more that I haven't heard before, then it's hard for me to give you marks. That thing is always there. Simon Tuja. Okay, so pollution control. Like our gentleman said there's always a self-cleansing least amount of flow you expect in a river. Our sewer ponds there, I haven't been there in years. But the last time I was there, they were not working as they should be. So our maturation ponds, just all those ponds over there, the facultative ponds, from NRDC you discharge there and then the science happens, mechanical science happens. Then a little bit clear water is the one that you discharge into your Kalikiliki stream. So even the engineers back then that were designing, they didn't just locate a place accidentally for the ponds. They did that for a very reason. Our fecal waste or our wastewater is going, it gets to be filtered in some type of way. It gets to a certain level of contamination. It's enough to be offloaded into the stream. Ideally, there should be someone reading the gauge measurements of the stream. Also, someone controlling the amount of effluent going into the stream. But the way things are at the moment, we just discharge everything there. But in a world perfect system, you gauge the amount of water levels that are passing through the stream. That water informs how much you can let waste into the stream. Because at the end of the day, like he said, you want to preserve the ecosystem, right? You cannot just offload. Okay. Last but not the least of these is determining reservoir capacity, all right? Reservoir capacity. So in a case when you are trying to design a reservoir, okay, because this is your reservoir, this is your dam, this is a reservoir. When you're trying to determine how much water you can impound, you want to know the least amount of waters you can have in that stream. So anything and everything in terms of a decision that you're making needs to be informed from a point of how does it look like when things are not well. So you can find enough information on that. All right, so let's write this after those 4 points. In considering the above design problems and others, in considering the above design problems and others that are not mentioned, in considering the above design problems and others that are not mentioned, the principal methods of low flow analysis are one, you have what you call the flow duration curve. Duration curve. You also have what is known as annual minimum series. Annual minimum series. Roy. Morning. Can I just call you in the next 30 minutes? I'm in a class. Okay, what's up? Annual minimum series. All right. The third method principle to analyze the low flow is called the partial duration series. Partial duration series. Okay? So all these are methods that you can use to analyze low flow of water. So after those 3, just right at the bottom, we will only consider the flow duration curve. we will only consider the flow duration curve. Flow duration curve. Okay. One of the best ways to study how the low flow duration curve works is just basically to do an example. So we'll do an example and then we'll try to understand what the example wants us to get out of it. Yeah. All right. So example. So I'm dictating. Flow data for a Okay. Flow data or data. Flow data for a proposed hydropower station is tabulated below. Flow data for a proposed hydropower station is tabulated below. Flow data for a proposed hydropower station is tabulated below. Okay, so this is the data. I think I need a phone for this. Okay, so this is the data given. We can hear that, madam. Okay, so example wants us to draw first of all the flow duration curve, but then you are given some values to work with. So we have what we call the mean daily discharge. And it's in Qmex. We know what Qmex are, yeah? What are Qmex? And then we also have what we call the frequency of occurrence. And this is in days. Okay? So we have more than 50. We have 50 to 40 to 40. We have a 40 to a 30, 30 to a 20, 22, a 10, and then we have less than 10. Okay, so this is how a typical question would look like. So one, I want you to just have this. So now the questions based on what you're given sound like this. Okay, there's a 50. Sorry, this is a 50. We have a 21, 132, 176, 191, 28, 5, and then 290. Okay, so the question one says draw the flow duration curve for the site. Draw the flow duration curve for the site. Draw the flow duration curve for the site. Okay, so this is how a question will just come. The first question is draw the flow duration curve for the site. This one, let's talk about that when you complete the whole questionnaire. Yeah. So call that A. B wants you to, if at least 10 cumecs, if at least 10 cumecs of flow is needed to generate a minimum power demand, if at least 10 cumecs of flow is needed to generate a minimum power demand. Are we there? I'll read that one more time. If at least 10 cumecs of flow is needed to generate a minimum power demand, how many days in a year will the power station? How many days in a year? Boss, simulemba. Or mnavisova kudala. Now I was talking to him. How many days in a year will the power station fail to meet the demand? How many days in a year will the power station fail to meet the demand? How many days in a year will the power station fail to meet the demand? Those two questions. So usually you have your 20 marks when you're able to do what we're about to do right now in the next 10 minutes. Are we together? So the first question, because they want you to draw the flow duration curve. It's from the curve that you will be able to analyze if or how many days in a year will this power station that you're designing be able to fail in a year. Are we together? So from the table, there are other values that you need to sort of get out of, and those values are going to help you to draw the duration curve. So this is one of those topics that requires you to have a graph, and we don't need that because we know how to manage that unless otherwise. But find time to, I'll give you a self-help question that you can just go and practice. Plot the graph, and then I'll show you how to read so that you determine how many days this power station, based on these values, will fail. So 1, you need to have your table, and it ends here. I always get students confused at some point because Tikasova, in the exam, they'll start asking, say the table is incomplete time. So let me state this for the record. This is where the example, the question ends. What follows is you needing to find those values, right? So 1, create a column, a row, a column, yes. Create a column that will talk about the cumulative frequency. We know what cumulative is, not so? And again, it should be in days. So we're just cumulating everything. So 21 plus the 0 on top there, the 21. 21 plus 132, 153. 153 plus the next value, 329. And then you do the same. This is a no-brainer, 805. And then the last one is 1095. Cumulative frequency of days. So you're just adding, so you're trying to find out the total number of days that are being considered, all right? And then the other column that you need to create is a cumulative Okay, so cumulative percentage. Let's just leave it at that. I don't like the way they use, they just replicated this. Okay, so whatever has been realized here, convert it into a percentage. Are we together? So how do you get your value here? So you're going to say your 21 divided by the total value, which is 1095 by 100%. That should be your 1.9%. Are we together? We are good mathematicians. I think I always say that. Okay? So the rest follows. So if you're going to do the same usual math, this is how you're going to fill up your table. You're going to have your 47. Can someone confirm this value if it's okay? Okay. So meaning you can do and you should do the same for the other columns, other rows. And then the last one should be 100%. Sometimes how you know that you're on the right track is to the last row, it should always be 100% because just this value divided by this value by 100. So it should always give you 100%. Okay? So once you have this value, just fill it up. You are done. I can erase, right? So I just need to illustrate something about the graph. We are almost done. Okay. Once you have these values, you can now draw the flow duration curve. And how do you go about it? So you need to plot something against something. And this is based on the values that you are getting. So you need to have your flow, and this is in cumex, okay, in cubic meters. And then you need to have your percentage. So let me say cumulative. Does NRDC clinic still work? I'm glad you didn't catch the joke. Okay. So, plotting should be easy, right? So what you're going to work with is based on the table that you've tabulated, you begin by saying, what is the first percentage, for instance? If this is my 0, maybe I'll mark this to be a 10, 20, 30, 40, 50. Your graduations are supposed to be informed by the values that are on the table. Are we together? You cannot have your maximum value as a 50 for the discharge flow, but then wind up at 200. Doesn't make sense, right? So leave it to just a point where it's enough for you to move. And then this is just like 100%. So you can always do a 10, 20, 30, 40, 50, 60, 90, and 100. And then you begin to plot. So the cumulative values, we have them. The flow, we also have it. So just to plot the first one, we have a 50, which is running against a 1.9%. So a 50 is just around here, okay? And then if this is your 10, this is your 5, probably your 1 is here. So your first point will be somewhere there. Are we together? The next point, make use of a 40 and the percentage. Whereas your 40 is somewhere down there. And your percentage is a 14. This is my 10, my 15 is here, so probably my 14 is somewhere there. And then you move on. At the end of the day, you should be able to plot something that looks like that. Yes, sir. Where we get it? Is the clinic still working? To start soon. Yes, sir. Okay, he's got a question. Okay. Are we okay on how we plot this and where the figures are coming from? So go and practice. Graph paper. I don't know if the department it has. I haven't seen one in a while, but you can always find something somewhere. When you plot, it should look like this, and probably this will give you about maybe a 10% or a 10 out of a 20, or maybe a half of that. But then the remaining bit is another part that is really interesting, and that's what you as engineers now are coming in to analyze and give the value. So the second question said, if at least 10 cumecs of the flow is needed to generate a minimum power demand, how many days in a year will the power station fail to meet the demand? What you want to do first is identify where your 10 cumecs are, because they are asking you, according to the flow, if the least amount of water you need for you to generate power starts at 10. It means that power can only be generated when we cut the line here going up. Anything below this does not work. Are we together? So you're going to draw your line, and it's going to hit somewhere here. What we are interested in is that when we draw a line to our curve, you beam it down to the cumulative percentage. This percentage is of interest to us, because that means that that's the percentage to which water or electricity can be generated when we've got water. Does that make sense? All right, so let me just repeat that. Your 10 is your minimum levels of water you can have in that river if you want to produce water. Meaning anything that's less than 10 cubic meters, you'll be in the load shedding space. So how do you find the days when in a year you want to have power? So you cut the line, get to a percentage, because these percentages are only going up to 100%. So you can relate 100% to the number of days in a year. Are we together? And if you can do that, then you can determine the percentage of a 75. So in short, before I write this, your 100%, because the question says how many days are you likely not to have power in a year? Your 100% relates to how many days are in a year? 365.5 days sometimes, right? But then what's going to become of a 75? Is this a 73%? 73.5%. That's the only math that you need to do, and that should inform you. So let's write this statement, all right, as a solution. Let's write this statement as a solution. The flow duration curve shows that 73.5% of the time the flow duration curve shows that 73.5% of the time, are we together? The flow duration curve shows that 73.5% of the time 10 cumecs is equaled 10 cumecs is equaled or exceeded for a given period. Ten cumecs is equaled or exceeded for the given period. Full stop. Okay? And we understand where the 73.5% is coming from, right? Good. So we add on a different statement to that. Therefore, comma, 26.5%, 26.5%, and this is coming from the fact that we can say 100% we subtract the 73.5. Therefore, 26.5% of the time, or 97 days. And how are we getting 95 days? So this is a 26.5% of a 365.5 days. So I said, therefore 26.5% which is that difference over there of the time, or 95 days. And how do we get the 95 days? It's just simple arithmetic, right? 26, 97. 97 days. Okay? Or 97 days, open bracket. How do we get that? It's just a 26% of the total number of days in a year, because that's what has been asked of us, making 1 year. If you want, you can stick to just 365 days, but it should show. So when you close the bracket, you can say, in a year, the power station will fail to meet the demand. In a year, the power station will fail to meet the demand. In a year, the power station will fail to meet the demand. Are we together? What this means is that you have, if I'm going to cut here, all these times by the Qmex, you have power. Your power station has enough to give and produce. The moment you hit that line, why? Because you are given the 10% as a low flow value that can generate power. The moment you hit that value, it means that everything and anything after that, this is what it means. Are we together? So fully understand this, because today they are asking you how many times will our design fail to supply power. The next question I can ask you is, how many days will this design be able to provide power? It's just the opposite, right? So it's the other end. Again, also, today I'm saying the lowest values that I want to produce water is 10 Qmex. Tomorrow I can raise it up and say the lowest value this design can have to produce power, let's say, is a 20. So things change. So you need to draw your line, it hits there, and then you come down. Whatever value will be there according to your accuracy of the design. And then you do the math, very simple arithmetic of what we've done there. Hey, ninakamba, ningasuna mvera pa. All right. Any questions? Where or which value is coming from? Where you lost? Sounds like it's clear. Yes, sir. The 10 is in the question, sir. Yeah. Yes, sir? 97. We agree where the 26 is coming from? From the 10, someone has asked a question. You come and fail to answer it. When someone is asking a question and I'm taking time to answer, I know it's important. The 26 was born because the 10 is in the question. When you project, what you're going to have is a 73 points. That's how much we can produce. But the difference to 100 is a 26. This is how much we can't produce. 26% of a year is 97 days. Yamveka? 26% of a year is 97 days. Any other question? So like I said, today is a 20, tomorrow it can be a 30. Just try to fully understand the concept.
When plotting the values this side, we're saying it's from a 50 to a 40, 42.
Yeah.
So we plot the maximum value
Yes.
against the
Yes.
calculator.
Mm-hmm.
Then when we reach 20, which is a 73%,
Mm-hmm.
now this side,
Mm-hmm.
we're plotting it against 10.
It's anything below. Remember the graph, the table said less than 10, huh?
It said 20 to 10. So So on the 73.5, it's at 20.
Mm.
So now the 20, we're plotting it against
Waluwa nawe.
7.9.
20 has got its own value,
Okay, which is
and then a 10 will also have its own value. And then there'll be a less than 10, right? Just get the max. You started with a 50, next should be a 40, 30, 20, 20, and then anything less. Any questions, guys? So I will generate a question a little bit that will require you to think. Don't be lazy to think. Because if you're expecting me to bring this in an exam, the same values, I'm not helping you, I'm killing you. Why? We never grow in comfort zones, so you need to find yourself in spaces that are very uncomfortable for you to grow. So I'll create something around what we've done, and then I'll send it through Madam Sally. All right, guys, so see you next week. Bye-bye.